In this example, we want to see if we have a consistent or inconsistent system. We have three equations with three unknowns representing three planes. So the first thing we do is we ask ourselves, like our handout says, are any of the normals parallel? Well, asking ourselves that question, we see that in fact none of the normals are parallel. And because of that, there are three possibilities. We either have one point of intersection, one line of intersection, or an inconsistent system creating a triangular prism. The way we're going to figure out which one that we have is to solve the system using matrices. So, using elementary row operations, we see that we can multiply row 1 by 5, row 2 by 7, and row 3 by 35 to set up the same numbers in the left-hand column of the matrix. We can then use elementary row operations and evaluate row 1 minus row 2 and row 1 minus row 3, and at the same time we can reduce row 1 back to what it originally was by multiplying through by 1/5. And that gets us to this row here. Now, hopefully we have good number sense and we can realize that these numbers here are all multiples of 4 and these numbers are all multiples of 185. So multiplying row 2 by 1/4 and row 3 by 1 over 185 leads us to have these as our new row 2 and row 3. Well, we can set up a 0 in this column, in this entry right here where the negative 2 is, by simply adding row 2 plus row 3. So we're going to leave row 2 alone, and we're going to do that. What ends up happening is we get 0, 0, 0, 0 in the bottom row. Well, there are an infinite number of solutions to the statement 0x plus 0y plus 0z equals 0. So that means there have to be an infinite number of solutions to our situation. And because there are an infinite number of solutions, we don't have one point of intersection and we don't have a triangular prism with no points of intersection. We have the only option that provides an infinite number of solutions, which is specifically a line of intersection. So we're going to figure out what the equation of that line is by referring back to our most recent matrix, and for purposes of what we're about to do, we can ignore that last row and treat it like we're just figuring out the line of intersection between these two planes, the first row and the second row. So we do that. We have 7, 3, 9, 20, and 0, 2, negative 1, 4. We can let y equal t. That'll be our parametric equation for y. Subbing that in to 2t minus z equals 4 leads us to z equaling 2t minus 4. We can plug that into the first row and solve for x. And we end up with x equaling negative 3t plus 8. So we have three parametric equations. X is negative 3t plus 8, y is t, and z is 2t minus 4. Putting these all together leads us to realize that the position vector is 8, 0, negative 4, and the direction vector is negative 3, 1, 2 for our line of intersection. And so what that means is that we have a consistent system. There are an infinite number of points on all three planes, all lying along the line r equals 8, 0, negative 4 plus t times negative 3, 1, 2, where t is an element of the reals.